Hey kids, Smath here. Got another part here, part 3 of our water and an introduction now to solutions. And so here are notes on solutions. Solutions have a unique property to them sometimes, and this property is called solvation. Not salvation, but solvation. That solvation is the interaction of a solute and a solvent. And the question is, how do we know if this solvation is going to happen, if a solvent will dissolve a solute? The answer here lies in the type of molecule. We learned about molecules polarity back in chapter 8, 7, and 8 when we did bonding. Well, now we're going to actually use that in regards to a solution. So the term that we use is like dissolves like. Polar solvents dissolve polar solutes. They also dissolve ionic things since we don't have many ionic solvents. So the more polar something is, the more polar a substance it will dissolve and or dissociate. Nonpolar things are going to dissolve nonpolar. And so we want to look at, will these things dissolve or go into solution? Will they exhibit the solvation effect? Well, if we have glucose in this first example, glucose is polar. Therefore, it's going to take a polar solvent of water, and that will dissolve. If we take glucose as a polar and try to dissolve that in a nonpolar solvent like oil, it won't dissolve. That's sucrose. That sugar will simply sink down to the bottom. It won't interact. There will be no solvation. So that's what happens with a polar. If we look at an ionic, sodium fluoride is very ionic, and that's put into water, polar solvents will dissolve an ionic thing. What won't water dissolve? Water won't dissolve nonpolar things. Nonpolar things would be ink. Oils are nonpolar things. So when we get ink on ourselves, that water won't dissolve it. It won't, and that's why when we get ink on our clothes, we need kind of a pre-wash like Shout to get that ink to dissolve. That's what happens. Now, what will dissolve that ink? Well, oil will dissolve that ink. And so if we put a nonpolar and a nonpolar, that's where we get. So remember, when we're talking about solutions, we're looking for like dissolves like. Now here are practice problems 15. If you're curious and you want some, we're making a transition from 15 into 16. I'm not assigning this, it's merely practice for you, but there are the problems and here are the solutions to those that are explained. Okay, those are there. Now I just want to go back and reiterate on dissociate or dissolve. We just did like dissolves like. Now we need to look at this and say, well, when it dissolves, is it truly dissolving and staying together in a solution, or is it dissociating and breaking apart? Well, here's what we have. We're going to take an ionic solute. Yes, the last example we had was sodium fluoride. This example, we have sodium fluoride, we have sodium nitrate. We put those into water. Those are ionics. Ionics are going to dissociate. They're going to break apart, and everything will become ions in solution. All ions in H2O are going to be considered aqueous, and ionic things in a polar solvent are going to dissociate. How do we know if something's ionic, though? Ionics are going to contain polyatomic ions, or they're going to have a high electronegativity difference. These are things that are very far apart on the periodic table, something from group 1, something from group 17. Those are our ionics. Ionics dissociate. Then we're going to have polar solutes. These are things that have an electronegativity difference. They're a little far apart. They're not way out on the edges, but they're a little far apart and they're polar. They may also be polar because they've got lone pairs on the central atom, or they're just asymmetrical. And because of that, these things are going to dissolve and not dissociate. They're polar. They're going to be consumed by the water. The water's going to surround it with that sphere and pull them all apart. but it's not going to dissociate into ions. Now, those are my two, ionic and polar. Now we move down to what happens with a nonpolar solute that we put into water, into a polar. In this case, nothing's going to happen. This is bromine. Bromine is one of the two elemental liquids, and it's very nonpolar. It has no electronegativity difference. And so when we put that into water, nothing happens. Okay? Nonpolar and polar do not mix. That's a good phrase right there. Okay? Remember, like dissolves like. Those two things, not going to happen. Okay? What now? That's what happens with our polar solvents and H2O. Now come down here and we have nonpolar solvents. Now our solvent is going to be oil. Oil is a great nonpolar solvent, really long chains of carbons. Well, if we put an ionic into it, that's basically the same thing as what we just did with our bromine, just the opposite. You're putting a very polar thing into a nonpolar solvent, and it's not going to break apart. No visible reactions going on there. Same thing with our polars. If we took, in this case, a brominated methane molecule, nothing's going to happen. That the ionic and polars do not mix. Okay? Now, my nonpolars, nonpolar solvent, nonpolar solute, this is going to dissolve. It can't dissociate because it's not made up of ions. It just stays together, and in this case, it's going from a liquid form to a solution form. We can't really say that it's aqueous. There's no water. We're just saying it's dissolved. It's a solution. So you could see that. You wouldn't write that completely out, but you would say SOLN. It's a solution state of matter. We don't know what that solvent was. That's why they write oil over the arrow here. So that's the lesson on dissolve, dissociate, or no visible reaction here. Okay, I'm Smath. I certainly hope that this video helps you. Our next video, we'll start talking about solubility and solubility curves.